Hello there, and welcome to Sleepy Science Vault. Somewhere out there, far beyond the light we can see, galaxies are moving. Not scattering outward with the gentle stretch of cosmic expansion, the way we've always been told the universe behaves. Something else. Something quieter. A slow, deliberate drift, in one direction. Together. As if pulled by a hand we cannot see. Welcome to the mystery of dark flow. For most of the night ahead, we're going to sit with this idea, turn it over slowly, the way you might turn a smooth stone in your palm in the dark. There is no rush here. Just the universe, and the strange quiet current that may be running through it. Let's begin at the beginning. Dark flow is the name astronomers gave to something they noticed in the motion of galaxy clusters, vast collections of galaxies, bound together by gravity, drifting through the cosmos in groups. Normally, we expect galaxy clusters to move in fairly random directions, carried along mostly by the universe's expansion, like leaves scattered on the surface of a slowly widening river. But dark flow described something different. Something that seemed almost coordinated. It was NASA that first brought this idea into public attention, describing an apparent large-scale motion of galaxy clusters, all seeming to stream in a common direction. Not scattering. Not random. Streaming. And the speed involved was staggering to consider. NASA's original report suggested these clusters were moving at roughly 1 million miles per hour. Try to hold that number in your mind for a moment. 1 million miles, every single hour, clusters containing thousands of galaxies, each galaxy containing billions of stars, all sliding through space together at a pace that dwarfs anything we experience in daily life. And yet, on the scale of the universe, this motion was subtle enough that it took careful, patient analysis of the cosmic microwave background, the faint afterglow of the Big Bang, to even notice it was there at all. What made the finding even stranger was what the motion seemed to be independent of. According to that original report, the cluster's motion appeared to be independent of the universe's overall expansion. This is an important distinction. The expansion of the universe is something we've come to accept, space itself stretching, carrying galaxies apart from one another like dots on the surface of an inflating balloon. But dark flow was not simply an artifact of that stretching. It seemed to sit on top of it, a separate motion, layered over the expansion like a current running beneath the surface of an already flowing river. And there was something else. The report noted that the effect did not fade as distance increased. Normally, in physics, we expect influences to weaken the farther out you look. Gravity grows fainter with distance, light grows dimmer, signals grow quieter. But dark flow did not behave this way. The pull, or whatever was causing this coordinated drift, seemed just as present in far-off clusters as in nearer ones. As though whatever was responsible was not a nearby, fading influence at all, but something vast. Something that didn't care how far away you measured from. It's easy to see why this idea unsettled so many astronomers when it first emerged. Dark flow is controversial, in large part, because the visible distribution of matter in the universe does not easily explain it. When scientists mapped out where galaxies, clusters, and known matter actually sit in space, nothing in that map seemed large enough, or positioned in the right way, to tug entire clusters of galaxies in a single unified direction. The visible universe, as far as we can map it, simply didn't offer an obvious answer. So naturally, theorists began looking outward. Or perhaps, more accurately, beyond. One interpretation offered was that something beyond the observable universe might be influencing nearby galaxy clusters. Beyond, in this case, is a heavy word. Not far away in the ordinary sense, but past the very edge of what we are capable of observing. The observable universe is limited by the speed of light and the age of the cosmos itself. There is a horizon we simply cannot see past, no matter how powerful our telescopes become. And dark flow raised the unsettling possibility that something on the other side of that horizon, some structure, some region of spacetime we will likely never directly witness, might be exerting a gravitational influence on the galaxies we can see. Try to sit with that for a moment. A force, reaching in from somewhere we may never be able to observe, nudging galaxy clusters across unimaginable distances, quietly, persistently, in the same direction. It's a beautiful thought, in its own eerie way. And also, a deeply uncertain one. Because it's important to say clearly, dark flow is described in astrophysics as a controversial hypothesis, not as an established fact. It is not a settled discovery sitting comfortably in textbooks. It's a proposed explanation, still being tested, still being argued over, still being re-examined every time new data becomes available. Some scientists have found supporting evidence in later observations. Others have looked at the same data and concluded the apparent motion may be the result of statistical noise, or subtle errors in measurement, rather than a real physical phenomenon at all. And so, later analyses and newer datasets kept the topic debated rather than fully settled. Which is, in some ways, exactly how good science is supposed to work. Not everything gets answered quickly. Some questions linger for years, decades even, quietly waiting for better instruments, better data, better ways of listening to the universe. So what, exactly, is dark flow trying to explain? At its core, it tries to explain something called peculiar velocities. In cosmology, peculiar velocity refers to the motion of a galaxy or cluster that is separate from the expansion of the universe, the leftover movement, so to speak, caused by gravitational interactions rather than the stretching of space itself. Most peculiar velocities are small, and mostly random, canceling each other out when you look at large enough scales. Dark flow proposed something different, an random pattern, clusters moving together, in alignment, rather than independently drifting in every direction. And this brings us to something worth remembering clearly, especially this early in our journey together tonight. Dark flow is not, itself, described as a new kind of cosmic force. It is not proposed as some exotic fifth fundamental interaction, sitting alongside gravity and electromagnetism. Instead, it is framed as a hypothesis for peculiar velocities, an attempt to explain a pattern of motion using the physics we already understand, just applied in a context we don't yet fully see. Whatever is causing it, if it is real at all, may still simply be gravity, just gravity reaching from somewhere unexpected. That's where we'll leave things, for now. A universe that may be drifting, ever so slowly, towards something just beyond the edge of what we can see, a pull with no clearly visible source, a debate that has quietly continued for years, without a final answer. Rest here for a moment, if you'd like. Let the scale of it settle over you slowly. Because ahead of us, there is much more of this mystery still waiting to unfold. Let's return to that idea of motion, the strange, coordinated drift we began exploring, and look a little closer at how scientists actually attempt to measure something so vast and so faint. Because measuring the movement of a galaxy cluster is not as simple as watching it cross the sky. Everything in this story is bound up in mathematics, in subtle signals buried within light that has traveled for billions of years. So let's slow down and understand it properly. In this idea, the measured velocity of a galaxy cluster isn't a single, simple number. It's described as the usual Hubble flow velocity, plus an extra, common direction component. The Hubble flow velocity is the familiar part. It's the motion caused by the expansion of the universe itself, the steady outward stretching that carries galaxies away from one another as space grows. Every cluster has this. It's expected. It's normal. It's the baseline hum of an expanding cosmos. But dark flow suggests there might be something layered on top of that baseline. An extra component. A shared motion, moving in the same general direction, present in cluster after cluster, as though riding quietly on top of the expansion everyone already agrees is happening. So to say it plainly, the measured cluster's speed, in this idea, equals the normal Hubble expansion, plus a possible extra shared motion. Two different things, tangled together in the same measurement. One expected. One, not so easily explained. Now, you might wonder, how would anyone even begin to separate those two signals? How do you look at a distant galaxy cluster and know which part of its motion is ordinary cosmic expansion, and which part might be this strange extra drift? The answer lies in something almost impossibly old. To judge whether this flow is unusual at all, scientists needed something steady to measure against. A reference point. Something that could, in principle, be treated as almost motionless, a backdrop against which everything else could be compared. And for this, they turned to the cosmic microwave background. The cosmic microwave background is the faint afterglow left over from the early universe, radiation that has been traveling through space since just a few 100,000 years after the Big Bang. It fills the entire sky, in every direction, incredibly faint and incredibly ancient. And because it's so uniform, so evenly spread across the cosmos, it can be used as the reference frame for judging whether a flow is unusual. In fact, this background radiation is often treated as something close to the ultimate cosmic reference frame for this kind of measurement. Not perfect, not absolute in some metaphysical sense, but about as close as physics allows us to get to a fixed backdrop, a still point against which the motion of everything else can be measured. If galaxy clusters are drifting relative to this ancient light, in a way that can't be explained by ordinary expansion alone, that drift becomes something worth paying very close attention to. And this is where galaxy clusters themselves become so valuable to cosmologists. Some cosmology references describe galaxy clusters as useful tracers of the universe's large-scale velocity field. think of them almost like buoys scattered across an enormous, invisible ocean. Individually, each one simply sits where gravity has gathered it. But together, their positions and movements can reveal the shape of larger currents running through the universe, patterns far too vast to notice by looking at any single cluster alone. So, how exactly did scientists go looking for this signal? They turned, once again, to the cosmic microwave background, but this time, searching not for its overall structure, but for tiny distortions within it. Subtle imperfections. Small deviations from the smooth, ancient glow that fills the sky. The key signal researchers focused on has a name, the kinematic Sunyaev-Zel'dovich effect, often shortened to the KSZ effect. It's a mouthful, I know. But the idea behind it is elegant, even beautiful, once you sit with it for a moment. As photons from the cosmic microwave background travel across the universe, they sometimes pass through galaxy clusters, vast clouds of hot, ionized gas surrounding those galaxies. And when that happens, the photons can interact with electrons in the gas, scattering slightly, shifting slightly, carrying with them a tiny imprint of the cluster's motion. This is, in fact, exactly how the original dark flow claim came about. Researchers studied how galaxy clusters affect the photons of the cosmic microwave background as that ancient light passes through them. It's a bit like watching how ripples in the surface of a pond are altered ever so slightly as they pass through a hidden current beneath the water. You don't see the current directly, but its influence leaves a trace. And what kind of trace, exactly? The effect shows up as a Doppler shift in the scattered background light. If you've ever noticed how the pitch of a passing ambulance siren changes as it moves toward you, then away from you, rising, then falling, you already understand the basic idea of a Doppler shift. Motion changes the wavelength of a signal, whether that signal is sound or light. In the case of the KSZ effect, if a galaxy cluster is moving toward us, the scattered light carries a faint signature of that motion. If it's moving away, a slightly different signature appears. These aren't dramatic, obvious shifts. They are incredibly small, subtle enough that detecting them requires extraordinarily sensitive instruments and painstaking statistical analysis across enormous numbers of galaxy clusters, patiently combined together. And this brings us to something worth sitting with for a moment, a detail that shapes how we should think about this entire mystery. The dark flow claim is based on tiny temperature shifts within the cosmic microwave background, not on directly photographing galaxies moving through space. No telescope has ever simply watched a cluster drift sideways across the sky in real time. This isn't that kind of observation. It's something far more delicate, reading faint fingerprints left behind in ancient light, fingerprints so small they exist only as fractions of a degree in temperature, scattered across data collected from countless points across the sky. It's a remarkable thing, really, that scientists can look at the faint leftover glow of the universe's infancy, search for imperfections smaller than we can easily imagine, and use them to ask whether entire clusters of galaxies might be drifting together towards something unseen. Whether that signal is truly telling us about a vast, coordinated motion, or whether it's an illusion born from the limits of our instruments and the complexity of our analysis, is a question we're going to keep circling gently, as this story continues. For now, Let this settle quietly in the back of your mind. Ancient light, faint temperature shifts, and the patient, careful search for a current running through the cosmos. There is still much more of this story ahead of us. So how did this all come together? How did a handful of researchers, sifting through faint signals in ancient light, arrive at something bold enough to be called dark flow? It started with using the motion of galaxy clusters as a probe. Not as an end in themselves, but as tools, instruments, in a sense, for detecting something much larger than any single cluster could reveal on its own. Each cluster, moving through space, carried within it a tiny piece of information. And by gathering enough of these pieces together, patiently, carefully, researchers hoped to assemble a picture of something vast, a picture no single observation could ever show alone. This phenomenon was first brought to wider attention through work that combined WMAP data with galaxy cluster measurements. WMAP, the Wilkinson Microwave Anisotropy Probe, was a satellite designed to map the cosmic microwave background with remarkable precision, capturing the faint afterglow of the early universe in extraordinary detail. It gave scientists a rich, detailed map of that ancient light, filled with subtle variations across the entire sky. Specifically, the original dark flow idea was based on MAP's 3-year data release. This was still relatively early in the mission, a snapshot of the sky built from 3 years of careful, continuous observation. Even at that stage, the data was detailed enough to search for the kind of faint distortions that the KSC effect might produce, small enough to be easily missed, yet consistent enough, perhaps, to reveal something real. But WMAP data alone wasn't enough. Researchers needed to know where the galaxy clusters actually were, where to look, so to speak, within that vast sky of ancient light. So the original analysis paired the cosmic microwave background data with something else entirely, the largest all-sky X-ray cluster catalog available at the time. Galaxy clusters, remember, contain vast clouds of hot, ionized gas, and hot gas emits X-rays. By cataloging clusters through their X-ray emissions, astronomers had built a map, a careful listing of where large clusters could be found scattered across the observable sky. That early, foundational study combined this X-ray cluster catalog with 3 years of WMAP data, layering one map of the universe over another. One map showing where galaxy clusters sat in space. The other showing the ancient light passing near and through them. And where those two maps intersected, where clusters sat against the backdrop of the cosmic microwave background, researchers searched for the telltale signature of motion. The Doppler-like shift. The faint fingerprint of the KSC effect. This is where our story reaches its true beginning, the moment when dark flow stopped being a quiet mathematical possibility, and became a public, startling claim. In 2008, a NASA-related study reported something remarkable. The signal they were seeing, this apparent coordinated motion, seemed to persist out to roughly 2.5 billion light-years away. Try, for a moment, to hold that distance in your mind. 2.5 billion light-years is a scale that stretches far beyond anything we experience in ordinary life, far beyond our galaxy, far beyond our local group of galaxies, out into a portion of the universe filled with countless galaxy clusters, each one a city of stars in its own right. And across that entire staggering distance, the signal did not fade. This is, in many ways, the heart of what made dark flow so puzzling to begin with. The reported motion was said to stay roughly constant with distance. In most physical phenomena we're familiar with, things weaken as they spread out. Light dims. Sound fades. Gravity grows weaker the farther you move from its source. But this stayed steady. Clusters 2.5 billion light-years away appeared to be moving in coordination with clusters much closer to us, as though the entire volume of observed space was being gently, persistently carried in a single direction, without any sign of the effect trailing off. And the coherence of this motion, the way it held together across such enormous stretches of space, was itself extraordinary. The reported bulk flow was described as coherent over at least 1 billion light-years. Coherent, in this context, means unified, moving together, in step, rather than scattered or random. 1 billion light-years is difficult to fully imagine. It would take light itself, the fastest thing in the universe, 1 billion years just to cross that distance. And within that colossal volume, whatever was happening seemed to be happening everywhere at once, in the same direction, with the same underlying pattern. This wasn't a handful of unusual clusters, either. The motion appeared to be coherent across hundreds of galaxy clusters, rather than just a few isolated anomalies. This detail mattered enormously to researchers, because science is often deeply suspicious of small samples. A handful of unusual clusters could easily be explained away: measurement error, an unlucky cluster of coincidences, a fluke in the data. But hundreds of clusters, spread across a vast portion of the observable sky, all seeming to drift in coordinated fashion, that was much harder to dismiss so easily. It's worth pausing here, in the quiet, to consider the sheer scale of what was being suggested. Hundreds of galaxy clusters, each one containing thousands of galaxies. Each one of those galaxies containing billions upon billions of stars, entire solar systems, entire possible worlds, swept up together in a single, silent current stretching across more than 1 billion light-years of space. Moving not randomly, the way ordinary cosmic motion tends to behave, but coherently. Together. As if answering some call we cannot hear. It's little wonder, then, that one early report described the flow as one of the largest coherent motions ever observed in the universe. Not the fastest motion ever recorded. Not the most energetic. But among the largest in sheer physical scale, in the sense of how much of the universe seemed to be swept up in the same quiet, persistent drift. This was the moment dark flow entered the wider scientific conversation. Not as a quiet footnote buried in a technical paper, but as a genuine puzzle, something that immediately drew attention, immediately invited scrutiny, immediately raised the question that we've been circling since the very beginning of this journey together. What could possibly cause something like this? If the visible universe, the galaxies, the clusters, the great cosmic web of matter we can map and observe, couldn't account for a motion this large, this coherent, this persistent across such staggering distances, then what could? It's a question that pulled at the edges of everything we thought we understood about the shape and structure of the cosmos. And it's a question that, even now, doesn't have a clean, settled answer. For a while, let yourself simply hold the image. Hundreds of galaxy clusters, spread across more than 1 billion light-years of space, quietly moving together in the dark, carried by something we still cannot clearly see or name. There's much more to uncover. Let's continue drifting gently through this mystery together. Let's stay with this for a while longer, because the deeper researchers looked, the stranger and more specific this motion seemed to become. The same body of work that first reported this coherent flow also confirmed something we touched on earlier, something worth returning to now with fresh attention. The flow was not explained by the visible matter distribution. Researchers had, by this point, mapped out where galaxies and galaxy clusters actually sit throughout the observable universe, forming what's often called the cosmic web, vast filaments and clusters of matter, separated by enormous, nearly empty voids. And when they checked that map against the direction and strength of this coordinated motion, the numbers simply didn't add up. Nothing in the visible structure of the universe seemed large enough, or arranged in the right way, to produce a pull this strong, this coherent, across such an enormous span of space. It's a strange kind of stillness, sitting with a mystery like that. All the tools of modern astronomy, all the careful cataloging of galaxies and clusters stretching across billions of light years. And yet, when researchers asked the visible universe to explain this motion, it simply didn't answer. And the scale of what needed explaining kept growing. NASA described this measurement as reaching nearly half of the observable universe. Let that settle for a moment. Not a distant corner. Not some isolated pocket of space. Nearly half of everything we are capable of observing, from the smallest nearby galaxies to the faintest, most ancient light at the very edge of what our instruments can detect. Half of the observable universe, potentially caught up in this same slow, coordinated drift. The individual clusters involved in this particular study were said to lie up to 6 billion light-years away. 6 billion years is longer than our own solar system has existed. Light we observe from clusters at that distance began its journey before Earth itself had even formed, traveling silently through the expanding universe for billions of years, only now reaching our instruments, carrying with it the faint imprint of motion from a time unimaginably distant from our own. And within that reach, the inferred bulk motion, the overall coordinated speed of this drifting matter, was calculated at nearly 2 million miles per hour. It's worth noticing how this number has grown, gently, as we've moved deeper into the story. Earlier, we spoke of roughly 1 million miles per hour. Now, in this analysis reaching further out into the depths of space, the estimate climbs closer to 2 million. Not because the universe suddenly began moving faster, but because different studies, using different data, different distances, different portions of sky, arrived at slightly different measurements of the same underlying puzzle. This is often how science moves forward, not through a single clean number arriving all at once, but through many careful attempts, each one refining, testing, and occasionally revising what came before. But here is where the puzzle deepens even further, and where it becomes genuinely difficult to explain away. Standard cosmological models predict that large-scale motions like this should decrease at greater distances. This is a fundamental expectation, built from decades of careful theoretical work. Structures in the universe form through gravity acting over time, matter clumping together, pulling on its neighbors, creating flows and currents that are strongest close to the source of gravitational influence, and weaker the farther out you measure. It's a bit like ripples spreading outward from a stone dropped into still water, strong near the point of impact, and gradually fading as they travel outward across the surface. According to everything we understand about how gravity shapes the universe, this kind of large-scale motion should behave the same way. Strong close to whatever is causing it. Weaker, fainter, more diluted, the farther away you look. And yet, this is precisely what dark flow seemed to defy. The motion didn't fade with distance the way theory expected. It appeared just as present at billions of light years away as it did closer to home. And that single, quiet inconsistency is, in many ways, the very heart of why this phenomenon captured so much scientific attention, and so much scientific skepticism, in equal measure. So, naturally, the next question becomes almost impossible to resist asking. If this vast portion of the universe truly is drifting together, coherently, persistently, without fading, then where, exactly, is it going? This is where our story turns toward direction. Toward a specific corner of the night sky, where researchers began to notice that this motion wasn't simply happening in some vague, unspecified way. It appeared to be pointing somewhere. The motion was described as extending roughly toward the southern constellations of Centaurus and Hydra. If you've ever looked up at a truly dark night sky, far from city lights, you may have noticed how the stars seem to organize themselves into patterns, ancient shapes that early astronomers used to navigate the heavens. Centaurus and Hydra are two such constellations, found in the southern sky, home to countless stars far beyond our own solar system. And it was roughly in this direction, this particular patch of the vast celestial sphere surrounding us, that researchers found this coordinated cosmic motion appeared to be heading. The direction of the flow was described as pointing along an axis centered near Centaurus and Hydra. An axis, in this sense, is like drawing an imaginary line stretching outward from our own position in space, through the sky, toward a particular target. And when researchers traced the direction of this coordinated motion across hundreds of galaxy clusters, spanning billions of light years, that imaginary line consistently pointed toward roughly the same region, this specific portion of the southern sky. One NASA description put it simply and vividly. The clusters stream along a path centered on Centaurus and Hydra. Stream is such an evocative word here, isn't it? Not scatter. Not wander. Stream, as though something as vast as hundreds of galaxy clusters, stretching across more than 1 billion light years, was behaving less like the random churn we might expect from an expanding universe, and more like water moving gently, purposefully, along a single unified current. NASA elaborated further, describing the clusters as seeming to move along a line extending from our own solar system toward Centaurus and Hydra. It's a strange thing, to imagine our own small corner of the universe, our sun, our planets, our quiet, unremarkable position among billions of galaxies, connected by an invisible line to this vast, unexplained cosmic motion happening far beyond anything we could ever directly touch or reach. Not that we are the cause of it, of course. Simply that, from our particular vantage point in the universe, this is the direction in which the pattern seemed to reveal itself, as though we happened to be standing at a spot where, for now, we can glimpse the trace of something moving. And this direction wasn't described as some enormous, vague region of sky either. It was remarkably specific. One NASA report described the clusters as heading along a 20-degree patch of sky. To put that into perspective, the full sky, spread out above and around us in every direction, spans far more than that. 20 degrees is a comparatively narrow window, a focused patch rather than some broad, diffuse area encompassing much of the heavens. For a motion involving hundreds of galaxy clusters, spread across billions of light-years of cosmic history, to align towards such a relatively narrow, specific direction, it added yet another layer to the mystery. It wasn't simply that things seemed to be moving in loosely similar directions. It was that they appeared to be converging, gently, coherently, toward this same particular corner of the night sky. Centaurus and Hydra, then, became more than simply constellations, more than the ancient patterns of stars used for navigation and storytelling for thousands of years of human history. In this particular story, they became coordinates. A direction. A quiet compass point at the far edge of what dark flows seemed to be suggesting. And of course, this raises the question that has been quietly building since the earliest moments of our journey together tonight. Is there truly something out there, in that direction, something beyond what we are capable of observing, gently drawing hundreds of galaxy clusters, and possibly nearly half of the observable universe, toward it? Or is the story more complicated, shaped as much by the limitations of our instruments and the complexities of measurement, as by any true underlying cause? We don't yet have a final answer. And in truth, we may not have one for a very long time. For now, simply let yourself imagine it. A vast, silent drift, stretching across the darkness, gently oriented toward a quiet patch of sky where two ancient constellations sit. Centaurus and Hydra, two small, ordinary points of light, standing, for now, as the quiet marker of one of the universe's most enduring mysteries. Rest here a while, if you'd like. There's no need to rush through wonder like this. Because our journey through this mystery is only just beginning to unfold. There's something worth pausing on here, before we move further into this story, a small but important detail about how science actually works when it comes to mysteries this large. Because as more researchers looked closely at this reported motion, the description of exactly where it was heading began to shift, ever so slightly, from one report to another. The reported bulk flow was, in some descriptions, refined even further, described as a 20-degree patch of sky located between the constellations Centaurus and Vela, rather than Centaurus and Hydra alone. It's a subtle distinction, but a meaningful one. Vela is another southern constellation, its name meaning sails in Latin, evoking images of ancient ships cutting quietly through dark water. And in some of the more detailed reporting on dark flow, this became the refined target, a region of sky nestled between Centaurus and Vela, rather than the broader area first described near Centaurus and Hydra. This is worth sitting with for a moment, because it tells us something honest about how discoveries like this actually unfold. Science rarely arrives at a single, perfect answer in one clean motion. Instead, it circles closer and closer to precision, gradually, through repeated analysis, refined instruments, and careful cross-checking. The clusters were reported to be moving toward a 20-degree wide region of sky, and exactly which two constellations best framed that region depended, in part, on which particular study, which particular dataset, and which particular team of researchers you were reading. In some reports, the flow was described as extending toward the sky region between Vela and Centaurus. In others, as we heard earlier, the emphasis fell more toward Centaurus and Hydra. Both descriptions point toward roughly the same general direction in the southern sky, a compact, 20-degree window, rather than some sprawling, imprecise region spanning much of the heavens. But the exact boundary, the exact framing, shifted slightly, the way the edges of a landscape might look slightly different depending on which hill you're standing on when you describe the horizon. This kind of subtle uncertainty is not a flaw in the science. If anything, it's a sign of honesty, researchers being precise about the limits of what their data could and could not tell them, rather than presenting an artificially tidy, oversimplified answer. And this brings us to something NASA itself was careful to emphasize, as this story continued to develop over the following years. NASA's later reporting described the flow as persisting to greater distances, rather than describing dark flow as a settled, finalized discovery. That word, persisting, is a careful one. It doesn't claim certainty. It doesn't declare the mystery solved. It simply acknowledges that, as researchers gathered more data, reaching farther out into the depths of space, the same puzzling signal kept showing up, again and again, refusing to fade quietly away the way many unusual results eventually do when subjected to closer scrutiny. But persisting is not the same as proven. And NASA was careful to make that distinction clear. In fact, one important NASA release stated plainly that the direction of the flow was less certain than the path itself. This is a subtle but crucial point, and worth slowing down to really absorb. Researchers felt reasonably confident that some kind of coherent motion, some axis, some overall pattern, was present in the data. The existence of an unusual alignment across hundreds of galaxy clusters was, by this point, a fairly robust finding, appearing again and again across multiple independent analyses. But exactly which direction along that axis the motion was truly pointing, that was less certain. The same report reiterated this distinction even more directly, noting that the direction is less certain than the existence of motion along the axis itself. In other words, imagine standing in a vast, dark field at night, and noticing, with reasonable confidence, that there seems to be a straight, invisible line running through the darkness in front of you. You can sense that the line exists. You can trace its general orientation. But you cannot yet tell, with full certainty, which end of that line represents the beginning, and which represents the destination. This leads us to one of the most quietly fascinating uncertainties in the entire dark flow story. Scientists noted that the data could not confidently determine whether the clusters were moving toward Earth or away from it. Sit with that for a moment. An axis, stretching across more than 1 billion light-years of space, involving hundreds of galaxy clusters, and researchers, despite years of careful analysis, could not yet say with confidence which direction along that axis the true motion was flowing. Was this vast portion of the universe drifting away from us, toward that patch of sky near Centaurus and Vela? Or, in some strange and almost dizzying possibility, could it be drifting toward us, with that same patch of sky simply marking the direction from which the motion appeared to be approaching? It's a bit like watching a very long, very slow-moving train from an impossible distance, so far away that you can perceive the direction of the tracks, but not yet tell whether the train itself is coming closer or pulling away. And to be clear, this wasn't a passing detail buried quietly in a technical footnote. The very same NASA report reaffirmed this uncertainty directly, stating that the data cannot yet say confidently whether the clusters are coming or going along that axis. This is real, acknowledged uncertainty, coming directly from the researchers and institutions closest to the discovery itself, not vague public confusion, but a genuine, honestly reported limitation in what the data could reveal. There's something almost poetic in that uncertainty, isn't there? A signal vast enough to involve nearly half the observable universe, and yet delicate enough, faint enough, that even its most basic directionality, coming or going, remained just out of reach of certainty. It would have been easy, at this point in the story, for dark flow to simply fade away. Many unusual astronomical signals, once subjected to years of scrutiny, additional data, and refined analysis, quietly dissolve into statistical noise or measurement error. Science is full of promising anomalies that eventually turned out to be nothing more than the limits of imperfect instruments, or chance patterns emerging from complex, noisy data. It would not have been surprising, or unusual, if dark flow had followed that same familiar path into quiet obscurity. But that is not quite what happened. Instead, as more data became available, the signal did something researchers found difficult to dismiss. It got stronger. A later study, using an expanded 5-year set of WMAP data, increased the total evidence available to researchers, and still reported a coherent flow. This was significant. 3 years of data had produced an unusual, unexpected signal. If that signal had simply been a fluke, a chance alignment of noise and coincidence, additional years of more detailed observation should have caused it to weaken, or scatter apart entirely, the way statistical illusions typically behave once subjected to more rigorous scrutiny. Instead, the coherent pattern remained. And this later update didn't just refine the existing data, it expanded the sample significantly. The updated study increased the total number of galaxy clusters under analysis to roughly 1,400. Let that number settle in your mind for a moment, especially in comparison to what came before. The original study, remember, had already found the signal present across hundreds of clusters, a substantial number, more than enough to raise serious scientific interest. But now, researchers were examining roughly 1,400 clusters, a considerably larger, more comprehensive dataset, offering far greater statistical strength to whatever pattern might, or might not, be present within it. And even with this expanded, more rigorous dataset, the coherent flow remained visible. This is often how real scientific mysteries behave, in contrast to simple illusions or statistical accidents. A false signal, born from chance or measurement error, tends to weaken, blur, or vanish entirely as more data accumulates, The way a faint shape glimpsed at the edge of vision often disappears entirely once you turn to look at it directly. But a real signal, if one truly exists, tends to do the opposite. It tends to sharpen, to hold its shape, to reappear again and again, even as the tools used to search for it become more powerful, more precise, more difficult to fool. Dark Flow, at this stage in its story, was behaving far more like the latter than the former. None of this, it's important to say clearly, proved beyond doubt that Dark Flow was real, in the fullest scientific sense. Uncertainty still remained, about the precise direction, about whether the clusters were approaching or receding, about the ultimate cause behind whatever pattern researchers were detecting. But the persistence of the signal, even as the dataset grew from hundreds of clusters to roughly 1,400, gave the mystery a certain durability, a weight, a seriousness, that quietly resisted the kind of quiet fading that so often marks the end of unusual scientific claims. It's worth imagining, for a moment, the researchers themselves during this period. Sitting with data stretching across billions of light-years of cosmic history, refining measurements, expanding datasets, testing and retesting an idea that stubbornly refused to disappear, even as they threw more scrutiny, more clusters, more careful analysis at it. There must have been a particular kind of quiet excitement in that, the sense of standing at the edge of something genuinely unresolved, genuinely mysterious, in an era when so much of the universe already feels mapped, catalogued, and explained. And yet here was something that simply would not resolve itself so easily. An axis in the sky. A patch of stars near Centaurus, near Vela, near Hydra, depending on which careful analysis you consulted. A flow, persisting across an ever-growing dataset, refusing to fade, refusing to fully reveal its secrets, refusing to confirm even something as fundamental as which direction it was truly moving. We'll continue following this thread very shortly, the growing body of evidence, the deepening mystery, and the questions that, even now, remain quietly unanswered above us, somewhere out past the edge of the visible sky. For now, let yourself simply rest in the not knowing. Some mysteries, after all, are not meant to be resolved quickly, and there is a certain peace in allowing this one to remain, for a little while longer, exactly as vast and unanswered as the universe itself. There is still so much more of this story waiting quietly ahead of us. Let's continue following the numbers for a while, because as this research progressed, the figures themselves became part of the story. Not just what was found, but how far, how wide, and how consistently the pattern kept reappearing. That later update, expanding on the earlier 3-year analysis, reported something worth pausing on. The flow, according to this new work, extended to about 2.6 billion light-years from Earth. If you're keeping track of the numbers we've encountered so far tonight, you may notice they've been shifting gently upward with each new study, 2.5 billion light-years in one report, now 2.6 billion in another. This is not the sign of a story falling apart. It's simply the ordinary texture of how science refines itself over time, one careful analysis layered gently over the last, each one adjusting the picture slightly as new data arrives. The expanded dataset used in this particular later study included roughly 1,000 galaxy clusters. a substantial jump from the hundreds examined in the very first analysis, though smaller than the 1,400 we encountered in the previous update. Different research teams, working with different data releases, different methods of selecting and verifying clusters, naturally arrived at slightly different totals. This is simply the nature of independent scientific work, multiple groups, approaching the same underlying mystery from slightly different angles, each contributing their own piece to a growing, evolving picture. Another report on this same period of research described something a little different still, an analysis using around 1,500 galaxy clusters, combined with 5 years of cosmic microwave background measurements. In this figure, 1,500 clusters paired with 5 years of WMAP data, appears again in a separate account from 2010, describing what was, by then, a considerably expanded and more thorough investigation. It's worth sitting with this pattern for a moment, rather than rushing past it. Study after study, year after year, research teams kept returning to this question with larger datasets, longer observation periods, more galaxy clusters folded into the analysis, 300, then hundreds more, then 1,000, then 1,400, then 1,500. Each time, more data. Each time, more scrutiny. And each time, the coherent flow remained. This growing body of evidence wasn't only measured in the number of clusters involved. It was also measured in distance, how far out into the universe the signal could still be detected. One later study reported that the signal extended to roughly 800 megaparsecs, considerably farther than an earlier estimate of around 300 megaparsecs. A megaparsec, for reference, is an enormous unit of cosmic distance, roughly 3.3 million light-years packed into a single measurement. So moving from 300 megaparsecs to 800 represents a truly significant expansion in how far this coherent motion appeared to reach into the depths of space. In fact, one NASA summary described this shift plainly and directly, stating that the dark flow signal reaches roughly twice the distance originally reported. Not a small refinement. Not a minor correction. A doubling. Whatever this signal truly represented, later, more careful analysis suggested it stretched across a volume of the universe roughly twice as vast as scientists had first estimated. And through all of this expanding distance, all of this growing dataset, the core finding remained remarkably stable. The NASA research team continued to report that the motion appeared to persist to about 2.5 billion light-years away, a figure that, across multiple studies and slightly varying methods, kept landing in roughly the same extraordinary range. 2.5 billion. 2.6 billion. Numbers close enough together that, on the vast scale of the universe, they describe essentially the same profound reach, a motion detectable not just nearby, not just within our immediate cosmic neighborhood, but stretching out across a meaningful fraction of the observable universe itself. And yet, even with all of this accumulating evidence, growing datasets, expanding distances, consistent detections across multiple independent studies, NASA remained careful, precise, and appropriately cautious in how it described the phenomenon. A NASA release on the subject stated clearly that dark flow remains controversial, because the matter we can see cannot explain it. This sentence carries real weight, and it's worth letting it settle slowly. This wasn't dismissive language. It wasn't a claim that the signal was fake or the result of simple error. It was, instead, an honest acknowledgement of a genuine scientific puzzle, a real, repeatedly detected pattern that our current understanding of the visible universe simply could not account for. Controversial, in careful scientific language, doesn't mean false. It means unresolved. It means real disagreement exists among serious researchers about what the data ultimately shows, and what it might mean. And dark flow, even as its evidence base grew larger and more robust with each passing year, remained firmly, honestly, in that controversial category. There's something worth appreciating in that honesty. It would have been easy, at various points in this story, for headlines to declare the mystery solved, to announce with confidence exactly what lay beyond the edge of the observable universe, tugging at hundreds, then over 1,000 galaxy clusters. But the actual scientific reporting, again and again, resisted that temptation. The signal was real, in the sense that it kept appearing, kept strengthening, kept surviving expanded datasets and additional years of observation. But its cause, its ultimate explanation, remains stubbornly, honestly, unresolved. It's also worth remembering just how significant this research was considered, even in its earlier stages, before some of these later expansions took place. Some coverage of the original work noted that the analysis of more than 1,000 galaxy clusters represented the largest study of its kind at the time. And in 2009, a New Scientist article echoed this same point directly, describing the analysis as the largest of its kind then available, built from data spanning over 1,000 galaxy clusters. Think, for a moment, about what that means in practical terms. This wasn't a small, speculative side project, tucked away in some obscure corner of astrophysics. This was, by the standards of the field at the time, a landmark undertaking, the most comprehensive dataset of its kind ever assembled for this particular question, drawing together the painstaking work of cataloging over 1,000 galaxy clusters, cross-referencing their positions with years of cosmic microwave background data, and searching, cluster by cluster, for the faint, consistent signature of coordinated motion. And through all of that immense effort, the pattern held. It's easy, sometimes, listening to numbers like these late at night, for the sheer scale of it all to blur together into abstraction. Billions of light years. Thousands of galaxy clusters. Megaparsecs stretching far beyond ordinary human comprehension. But underneath all of these numbers is something remarkably human, in its own way, researchers, patiently gathering data year after year, refining their methods, expanding their samples, testing and retesting an idea that, by every reasonable expectation of how false signals typically behave, should have quietly faded away. Instead, it grew stronger, more detailed, more far-reaching, and, in its own way, more mysterious. We are, even now, still standing at the edge of an unanswered question. A flow, reaching outward across billions of light years, involving well over 1,000 galaxy clusters, consistently pointing toward the same general direction in the southern sky, and no confirmed explanation, drawn from the visible universe, capable of fully accounting for it. let yourself rest in that unresolved space for a little while, if you'd like. Not every mystery needs to be solved immediately to be worth sitting with quietly, turning over slowly in your mind as the night continues on around you. Because ahead of us, there is still much more of this story left to explore. Now we arrive at the question that has been quietly waiting beneath everything we've discussed so far tonight. If the visible universe cannot explain this motion, then what can? This is where dark flow stops being simply a puzzle of measurement and becomes something closer to a genuine philosophical frontier, a place where careful science begins to brush up gently against the very edges of what we can know at all. NASA itself drew a comparison here, one worth sitting with carefully. The agency explicitly compared dark flow to other dark mysteries in modern cosmology, dark energy, and dark matter. These are names we've grown almost familiar with over the past few decades, even though what they represent remains largely unknown. Dark matter, the invisible substance that seems to outweigh all the visible stars and galaxies combined, revealing itself only through its gravitational influence. Dark energy, the mysterious force appearing to accelerate the expansion of the universe itself. Both are called dark, not because we understand them and simply can't see them, but because we don't yet know what they truly are. We know their effects. We don't know their nature. Dark flow, in NASA's framing, belonged in that same quiet, humbling category. Not a mystery we had solved and simply given an evocative name to. A mystery we could measure, but not yet explain. So where might an explanation come from? One of the most striking ideas offered by the NASA research team involves something from the very earliest moments of the universe's existence, an event known as inflation. According to leading cosmological theory, in an unimaginably brief fraction of a second after the Big Bang, the universe underwent an extraordinarily rapid expansion, stretching space itself outward at a pace far faster than anything we experience today. The NASA team suggested that inflation could have pushed the matter responsible for dark flow beyond the observable universe entirely. Let that idea settle slowly, because it's a profound one. If inflation truly did stretch space this dramatically in the universe's first fleeting moments, then it's entirely possible that some matter, some structure, originally close to what would eventually become our observable universe, was carried outward by that expansion, flung beyond the boundary of what we could ever hope to see, even with our most powerful instruments. Not destroyed. Not gone in any absolute sense. Simply placed permanently beyond our cosmic horizon, separated from us by a gulf that even light, given the entire age of the universe, has not had time to cross. And if such matter exists out there, beyond that horizon, its gravity might still, in principle, reach back toward us. Gravity, as far as we understand it, doesn't require light to travel between 2 points to have an effect. It could, theoretically, still tug gently on the structures within our observable universe, even if we can never directly see the source of that pull. This leads to something quietly remarkable, the idea that the dark flow measurement itself might offer a way to probe the cosmos before inflation. Normally, when we talk about observing the universe, we're limited to what light can show us, and light cannot show us anything from before this dramatic period of early expansion, because the universe as we can observe it essentially began, in a very real sense, at that moment. But if dark flow really does trace the gravitational influence of matter pushed beyond our horizon by inflation, then this faint, coherent motion might be doing something extraordinary, offering us the faintest possible echo of conditions that existed before inflation itself. Not an image, not direct light, but perhaps a gravitational whisper, reaching us from a time and a place otherwise entirely closed off from observation. Some explanations extended this line of thinking even further, connecting dark flow to conditions that may have existed before cosmic inflation began at all. It's a delicate, almost dizzying thought, using the motion of galaxy clusters, billions of light years away, as a kind of distant, indirect window into the state of the universe in its very first, almost unimaginable moments. Given all of this, it's not surprising that some scientists interpreted the result as possible evidence for structure existing beyond the visible edge of the universe. Not empty space out there, beyond what we can observe, but genuine structure. Matter. Massachusetts. Perhaps even entire regions resembling, in some form, the universe we know, simply placed forever beyond our reach by the vast, expanding gulf of space and time. One specific explanation proposed that the clusters could be responding to a very large mass located outside the observable universe. A single, enormous source of gravitational influence, vast enough, massive enough, that its pull could still be felt even from beyond the very boundary of what we are capable of detecting directly. We would never see this mass. We could never point a telescope toward it and capture its light. We could only infer its presence, indirectly, through the quiet, persistent drift it seems to leave behind in the motion of everything nearby. From here, the ideas begin to stretch even further into speculation, carefully, cautiously, but unmistakably into territory that borders on the edge of established physics. One more speculative idea suggested that neighboring bubble universes could be influencing matter within our own universe. This concept draws from certain theoretical models of cosmology, in which our universe might not be the only one, but rather one bubble, one region, existing alongside countless others, each forming through their own separate inflationary events, each potentially vast and complete in their own right, yet separated from one another by unimaginable distances, or perhaps by dimensions we don't fully understand. In this framework, it's theoretically possible that a neighboring bubble, existing just beyond the edge of our own, might exert some faint gravitational influence on the structures within our observable universe. This is, without question, one of the more speculative branches of the broader dark flow conversation. But it's a thread worth mentioning honestly, because it did emerge as one genuine possibility discussed among researchers exploring what might lie behind this unusual signal. Taken together, these ideas led to something remarkable: dark flow being presented, in certain discussions, as a possible hint that our universe might be part of a larger multiverse. Not a proof. Not a confirmed discovery. A hint, a faint, indirect suggestion, emerging from the careful measurement of galaxy cluster motion, that perhaps our universe is not alone. That perhaps, somewhere beyond the boundary we can never cross, other regions, other bubbles, other expanses of space and structure, might exist as well, occasionally leaving the faintest gravitational trace upon our own small corner of everything. It's worth pausing here and simply sitting with the strangeness and the beauty of that idea for a moment. Another suggested possibility, sitting somewhere between these more exotic multiverse concepts and simpler explanations, proposed that the source of this influence could be something like a gigantic singularity. A singularity, in physics, describes a point where the known laws of physics as we understand them seem to break down, conditions of such extreme density that our current models struggle to describe what's truly happening. The idea that an enormous singularity, existing somewhere beyond our observable universe, might be exerting a distant gravitational pull, offered yet another possible thread researchers considered while trying to make sense of this signal. And other descriptions tied the signal to matter expelled shortly after the Big Bang itself. Rather than invoking other universes or exotic singularities, this explanation stayed a bit closer to more familiar territory, suggesting that ordinary matter, present in the earliest moments following the Big Bang, might simply have been flung outward with such force and speed that it now lies beyond our observable horizon, its gravity alone reaching back across the ages to gently influence the structures we can see. What's striking, listening to all of these possibilities together, is how wide the range truly is. On one end, relatively grounded ideas, ordinary matter, expelled early in the universe's history, now sitting just beyond our observable reach. On the other end, ideas that stretch toward the most speculative frontiers of theoretical physics, other bubble universes, entire hidden regions of a vast and largely unknowable multiverse, quietly nudging our own corner of reality. In dark flow, this faint signal traced through subtle temperature shifts in ancient cosmic light, sits somewhere in the middle of all of it, a genuine measurement, repeated and refined across multiple independent studies, pointing toward a mystery large enough to comfortably hold every one of these explanations, without yet confirming any single one of them as correct. It's a rare kind of scientific moment, in truth. A real signal, carefully measured, persistently reappearing, standing at the threshold of ideas so vast, so far-reaching, that they touch questions philosophers and scientists alike have wondered about for generations. Is our universe truly alone? Is there something, anything, beyond the edge of everything we can ever hope to observe? And if there is, could its presence ever leave a trace gentle enough, subtle enough, to reach us, not through light, which cannot cross that boundary, but through the quiet, patient language of gravity alone? Let yourself rest in that question for a while, if you'd like. There's no need to settle on a single answer tonight. Some questions are simply meant to be held quietly, turned over slowly in the dark, without any pressure to resolve them all at once. Because our journey through this mystery is still only 2/3 of the way complete, and there is a great deal more still waiting for us, just ahead. As with any great scientific mystery, dark flow did not exist in isolation. Other researchers, working with entirely different methods, entirely different types of data, began to approach the same fundamental question from new angles. And what they found added yet another layer of complexity to a story that already seemed to resist easy answers. In 2012, a study took a very different approach to searching for this kind of cosmic motion. Rather than relying on the cosmic microwave background and the subtle KSC effect we explored earlier, this research turned instead to supernovae, the brilliant, explosive deaths of massive stars, visible across enormous distances, and often used by astronomers as reliable markers for measuring cosmic distances and motion. This supernova-based study did find evidence of a one-directional flow. But it was, in a very real sense, a much gentler, quieter version of the story we've been following so far. The motion detected in this analysis was considerably slower than what earlier galaxy cluster studies had reported. According to a National Geographic summary of the findings, this slower flow measured at approximately 550,000 miles per hour. If you recall the earlier figures we discussed, nearly 1,000,000 miles per hour in the original analysis, climbing toward almost 2 million in later, more extended studies, this new number sits notably lower. Still an extraordinary speed, by any ordinary human standard, but far more modest, far closer to what standard cosmological models might comfortably expect, than the far larger figures reported in the original dark flow research. And the distance involved told a similarly more modest story. This supernova study detected motion only out to about 240 million light-years from Earth. Compare that gently, for a moment, to the numbers we've grown familiar with over the past several segments: 2.5 billion light-years, 2.6 billion light-years, even reports stretching toward reach nearly twice the earlier estimates. 240 million light-years, while still an enormous distance by any everyday measure, represents a comparatively small, nearby volume of the universe, a much smaller stage on which this newly measured motion appeared to be unfolding. Perhaps most significantly, the researchers behind this 2012 study reached a notably different conclusion about what their findings actually meant. They argued that this result remained consistent with standard cosmology. Unlike the earlier dark flow claims, which described a motion that seemed to defy conventional theoretical expectations, refusing to fade with distance, spanning nearly half the observable universe, this supernova-based motion fit comfortably within the range that existing cosmological models already anticipated. No mysterious force required. No structure beyond the observable universe necessary to explain what they were seeing. So if this motion could be explained within the boundaries of standard, well-understood physics, what did the researchers propose was actually causing it? Rather than looking toward exotic explanations beyond the edge of the observable universe, the study's authors suggested a much more local, more grounded possible cause. They proposed an internal explanation, something like the gravitational influence of a nearby supercluster, a large but entirely ordinary concentration of galaxies, close enough to still be well within our observable universe, simply massive enough to gently tug on its surrounding structures. It's worth pausing here and appreciating just how differently this particular study framed the broader mystery. Where the original dark flow research pointed toward the unexplainable, toward possibilities stretching into inflation, multiverse theory, and structure beyond our cosmic horizon, this supernova-based study suggested something far more familiar. Perhaps what we'd been observing, at least in part, was simply the recognizable fingerprint of nearby cosmic structure, gravity behaving as gravity always does, just on a scale large enough to occasionally surprise us. This divergence between studies, using different methods and arriving at somewhat different conclusions, is itself an important part of how real scientific mysteries unfold. Different techniques carry different strengths, different limitations, different sources of potential error. A finding that shows up consistently across multiple, truly independent methods becomes much harder to dismiss. But a finding that appears strongly in one method, and much more modestly, or differently, in another, invites careful, patient reconsideration. And this reconsideration, for dark flow, was about to deepen even further. Because 2 years later, in 2014, an entirely new player entered this unfolding story, one carrying with it some of the most advanced instrumentation ever built for observing the cosmic microwave background. This was the Planck satellite, a mission developed by the European Space Agency, specifically designed to map the ancient light of the early universe with extraordinary precision that, in many respects, surpassed even the capabilities of WMAP, the instrument at the heart of the original dark flow discovery. In 2014, a Planck-based analysis reported something striking, and, for many following this story closely, genuinely unexpected. The dark flow signal, according to this new analysis, does not exist. Let that settle for a moment, especially after everything we've explored together tonight. After years of growing datasets, after the signal persisting through an expansion from hundreds of clusters to over 1,000 to nearly 1,500, after the detected distance seemingly doubling from roughly 300 megaparsecs out to 800. After careful researchers, again and again, found the coherent motion holding steady, refusing to fade the way statistical illusions typically do. And now, this new analysis, using more advanced instrumentation, was reporting that the signal simply wasn't there at all. It's important to understand exactly how this new study approached the question, because the details matter a great deal here. This Planck-based analysis used the very same cluster sample as earlier dark flow research. This wasn't a case of entirely new galaxy clusters being introduced, potentially explaining away the difference through simple sample variation. Researchers deliberately returned to the same clusters previously examined, the same regions of sky, the same fundamental structures, but this time, paired with far more sensitive cosmic microwave background data. And the improvement in that data was substantial. The Planck instruments carried significantly higher spatial resolution and greater overall sensitivity than the earlier WMAP satellite had offered. Where WMAP had provided the foundational data used to first detect dark flow, Planck represented a genuine technological leap forward, capable of measuring far finer details in the cosmic microwave background, capable of distinguishing subtle patterns with a level of precision simply unavailable to the earlier mission. Using this considerably more refined instrument, the Planck satellite's later results did not find evidence for the flow at the scale originally claimed. The same galaxy clusters, a more sensitive lens through which to examine them, and, this time, no coherent signal strong enough to support the original, striking claims about a vast, coordinated cosmic motion. This wasn't a small or hastily conducted follow-up study, either. The Planck analysis was carried out by a substantial team of researchers, 175 scientists in total, working together with data gathered by the European Space Agency's flagship mission. This was a large, carefully coordinated scientific effort, bringing considerable expertise and rigorous methodology directly to bear on the specific question that had captivated so much attention since the original 2008 findings. It's worth sitting quietly with this turn in our story for a moment, rather than rushing past it toward easy resolution. For years, dark flow had behaved in a way that seemed to defy the usual pattern of statistical illusions, growing stronger, not weaker, as more data accumulated. And now, an even more advanced, even more sensitive set of instruments, examining the very same patch of universe, was suggesting that perhaps the underlying signal simply wasn't as substantial as earlier research had proposed. Does this mean the mystery is resolved? Does this mean everything we've explored together across the previous segments of this journey was simply an illusion, eventually corrected by better technology? The honest answer, as we're about to discover, is considerably more nuanced than that. Because science, especially at frontiers this delicate, rarely delivers a single, final verdict all at once. And the story of dark flow, even after Planck's striking findings, was far from finished. Let's rest here for just a moment, with this new uncertainty settling gently over everything we've learned so far. A signal that seemed so persistent, so resistant to easy dismissal, now facing its most serious challenge yet, from the most sensitive instrument ever built to examine it. There is still more to this story, and we're about to see how it continues to unfold. Let's stay with the Planck findings a little longer, because there's more detail worth understanding before we can fully appreciate what this new evidence actually meant for the broader mystery we've been following all night. The Planck research team didn't rely on a single method of analysis to reach their conclusion. Instead, they described conducting what they called a multi-pronged analysis, approaching the question from several different angles simultaneously, cross-checking their results using multiple independent techniques rather than depending on just one line of evidence. And across all of these approaches, the team reported finding no evidence of galaxy clusters streaming coherently in the way earlier research had claimed. This phrasing, streaming coherently, echoes directly back to where our story began tonight, doesn't it? That very first description of dark flow, of galaxy clusters seeming to move together, in unison, toward a shared direction. And now, this same fundamental claim, the coherent streaming at the very heart of the original discovery, was being directly challenged by a team using considerably more advanced instrumentation. One summary of this Planck-based work reinforced the point with similar clarity, stating simply that the newer data found no evidence for clusters streaming coherently. Not a subtle refinement. Not a minor downward adjustment to the original figures we explored earlier. A direct challenge to the core claim itself. But it's important to notice exactly how careful, and exactly how precise, this new finding actually was. Because the Planck team didn't simply declare that dark flow was entirely impossible, full stop, in every conceivable form. Instead, the 2014 analysis set what's known as an upper limit, a boundary describing the maximum possible speed such a flow could have, if it existed at all, while still remaining consistent with the newer, more sensitive data. That upper limit was calculated at 254 kilometers per second. To help place that number in context, alongside the far larger figures we've discussed throughout our journey tonight, this upper limit is several times smaller than the speed claimed in the original dark flow reports. Where earlier studies had suggested speeds approaching 1 million, and even nearly 2 million miles per hour, this new analysis suggested that if any hidden flow does exist at all, it would need to be considerably gentler, a small fraction of what had originally captured such widespread scientific attention. This distinction matters enormously, and it's worth sitting with carefully. An upper limit doesn't necessarily mean absolutely nothing is happening out there. It means that whatever might be happening, if anything at all, must be far more modest than originally proposed, quiet enough, subtle enough, to have remained hidden even within Planck's considerably more sensitive measurements. Given how deeply this new result challenged the foundations of the original dark flow claims, it's perhaps unsurprising that the implications reached well beyond astrophysics alone, touching some of the more speculative territory we explored together in our previous segment. The Planck result was described, in some discussions, as closing off a potential route to evidence for a multiverse. Remember, earlier in our journey, we spoke of dark flow being interpreted by some researchers as a possible hint, a faint, indirect suggestion that our universe might not be alone, that other bubble universes, existing beyond our own, might be gently influencing the structures we can observe. If dark flow, as originally measured, wasn't truly present in the way early research suggested, then this particular avenue toward multiverse evidence, this specific thread of reasoning, built upon the observed motion of galaxy clusters, became considerably less compelling. Not eliminated as a broader theoretical possibility, but this particular observational pathway toward supporting it, quietly closed, or at least, very significantly narrowed. So, given everything we've explored together tonight, the original bold claims, the years of expanding evidence, and now, this serious and sophisticated challenge from Planck, where does the scientific community actually stand on dark flow today? The honest answer is nuanced, and worth exploring carefully, rather than settling for a simple, tidy conclusion in either direction. Some researchers today treat dark flow mainly as a historical controversy, rather than as a currently accepted phenomenon. This framing is significant. It doesn't necessarily mean the original researchers were wrong, in some absolute sense, or that their careful analysis was flawed. It simply reflects where the weight of evidence currently sits, particularly following Planck's more sensitive examination of the same underlying data. Dark flow, for many in the field today, has become something closer to a fascinating chapter in the ongoing story of cosmological research, a bold, carefully reasoned claim that captured enormous attention, inspired years of careful follow-up investigation, and ultimately, faced serious challenges from more advanced instrumentation. And yet, the story clearly hasn't been fully closed, either. Because dark flow continues to appear, meaningfully, in ongoing scientific literature. A later review paper noted that dark flow is often discussed in direct connection with the kinematic Sunyaev-Zel'dovich effect, the very same subtle Doppler-like signature within the cosmic microwave background that we explored earlier, the foundation upon which the original dark flow claims were built. This connection persists in the scientific literature, even now, because the underlying method, searching for coherent motion through this particular signal within the cosmic microwave background, remains a legitimate, actively used technique in modern cosmology, regardless of how the specific original dark flow claims have ultimately been evaluated. In fact, the original dark flow work continues to be discussed alongside the Sunyaev-Zel'dovich effect in later scientific reviews, treated as an important historical case study. An early, ambitious attempt to use this particular method to search for large-scale coherent motion across the universe, an attempt that, whatever its ultimate conclusions, helped shape and refine how later researchers approached similar questions. And remarkably, even in more recent, careful review literature, specific figures from the original claims continue to be documented and discussed. The same review noted that the hypothesized flow could extend to roughly 800 megaparsecs or more, the very same expanded distance estimate we encountered earlier in our journey, still being carefully recorded and considered within the broader scientific conversation, even as its ultimate validity remains genuinely contested. That same review even documented the precise proposed direction of this claimed flow, using a very specific method astronomers rely on for describing locations across the sky, galactic coordinates. According to this review, the hypothesized direction sits at approximately L equals 283 degrees, B equals 12 degrees. Galactic coordinates like these allow astronomers to pinpoint an exact location relative to the plane of our own galaxy, offering a level of precision far beyond simply naming nearby constellations like Centaurus, Hydra, or Vela. It's a small but meaningful detail, this exact coordinate, a reminder that behind all of the broader narrative we've explored tonight, real, careful, precise scientific measurement sits quietly at the foundation of this entire mystery. So where does this leave us, as our journey continues gently onward into the night? Dark flow exists today in a genuinely fascinating, unresolved space. Not fully confirmed. Not fully rejected, either. A bold, carefully measured claim from the original research, built upon expanding datasets that seemed, for years, remarkably resistant to fading away, now facing a serious, sophisticated challenge from more advanced instrumentation, suggesting that if any real signal remains at all, it must be far more subtle than first proposed. And yet, the underlying question, whether structures beyond our observable universe might, in some way, leave a gentle, gravitational trace upon what we can actually see, remains a legitimate, actively discussed area of cosmological inquiry, even now, even after Planck's careful re-examination. Perhaps this is simply the nature of frontier science, when working at scales this vast, and with signals this delicate. Certainty arrives slowly, if it arrives at all. And sometimes, what we're left with, even after years of careful, dedicated research, is not a final answer, but a deeper, more refined understanding of exactly how much remains quietly unknown. Let yourself rest gently in that uncertainty for a while, if you'd like. There's a certain peace, I think, in accepting that not every mystery the universe presents to us needs to be fully solved to remain worth exploring. Because our journey together tonight is not yet finished, there is still more of this story softly waiting, just ahead. Before we bring this long night's journey to its close, there's one more piece of the puzzle worth examining carefully, a detail that helps explain, perhaps better than anything else we've discussed, why this signal proved so difficult to simply dismiss, even in the face of Planck's serious challenge. That same later review noted something crucial about the scale of the original claim. The proposed signal, if real, would be much larger and more coherent than standard cosmological models, specifically, what's known as the lambda CDM model, would typically expect. This model, often simply called the Standard Model of Cosmology, represents our current best understanding of how the universe is structured and how it evolves, incorporating dark energy, cold dark matter, and the gradual, gravity-driven formation of cosmic structure over billions of years. Within this framework, motions on the scale originally claimed for dark flow, coherent, persistent, spanning well over 1 billion light-years, simply weren't expected to occur naturally, at least not with the strength and consistency that the earliest research reported. This is, in many ways, exactly why the original claim mattered so much, and why it demanded such careful, sustained scientific attention. It wasn't simply an unusual measurement. It was a measurement that, if accurate, sat meaningfully outside what our best, most thoroughly tested cosmological theories predicted should be possible at all. Now, as we settle into this final part of our journey together tonight, let's take a moment to gently gather the threads of this story, and consider where dark flow truly stands. The phenomenon, as we discussed very early on, was named dark flow quite deliberately, chosen specifically to echo the language of dark matter and dark energy. Three great unknowns, sitting quietly alongside one another in modern cosmology, each one representing something real that we can measure, in some indirect way, and yet something whose true nature continues to elude us. It's a fitting name, in the end. Not a name that claims understanding. A name that honestly admits the absence of it. Later NASA reporting continued to link this signal to clusters moving at speeds exceeding 1 million miles per hour, a figure that, across all of the refinements and revisions we've followed throughout tonight's journey, remained a kind of touchstone. The number around which so much of this story has quietly orbited. And amid all of the vast statistics, the billions of light years, the shifting cluster counts climbing into the thousands, it's worth pausing to remember that behind every one of these measurements sit real, individual objects, actual galaxy clusters, with their own names, their own specific place in the sky. One 2009 summary of this research specifically mentioned a cluster known as 1E0657-56, describing it as among the hundreds involved in this reported coherent motion. You may recognize this cluster by another name entirely. It's more commonly known as the bullet cluster, famous in its own right within astrophysics as one of the most compelling pieces of evidence for the existence of dark matter, observed through the dramatic separation of visible matter and gravitational mass during a massive cluster collision. That same summary placed this cluster at a staggering distance, roughly 3.8 billion light-years away from Earth. It's a quiet, almost poetic detail, discovering that a cluster already famous for one great cosmic mystery also became a small part of another, entirely different mystery, woven together, simply by its position, deep within this story of dark flow. To fully appreciate how unusual, or perhaps how plausible, these reported cluster velocities truly were, it helps to look back at some of the broader theoretical work already existing within cosmology, well before dark flow itself became a subject of focused research. Older theoretical work had already noted that cluster velocities can reach around 2,000 kilometers per second in some cosmological models. This is a meaningful figure to hold alongside everything else we've discussed tonight, because it tells us that fast cluster motion, in itself, isn't necessarily strange or unprecedented. Individual clusters, under certain theoretical conditions, were already understood to potentially reach quite significant speeds. That same body of older research also noted that clusters can display strong attractive motions on small scales, meaning that, at least locally, within relatively confined regions of space, galaxy clusters were already known to sometimes move toward one another with considerable force, drawn together by concentrated gravitational influence from nearby massive structures. What made dark flow different, then, wasn't simply the existence of fast cluster motion. It was the coherence, the sense that so many clusters, spread across such an enormous volume of space, seemed to be moving together, in the same general direction, rather than displaying the kind of localized, small-scale attraction that theoretical models had already comfortably anticipated. In fact, large-scale cosmological simulations typically predict something quite different from perfect, universe-spanning coherence. These simulations often predict what's called a Maxwellian distribution of cluster velocities, a statistical pattern where cluster motions are expected to vary somewhat randomly around an average value, similar to how the speeds of individual gas molecules in a container tend to distribute themselves around a typical value, rather than all moving in perfect, coordinated unison. In other words, standard theory generally expects a certain amount of healthy, natural randomness in how galaxy clusters move relative to one another, not the kind of large-scale, coherent streaming that the original dark flow claims described. Interestingly, theoretical comparison work examining these kinds of cluster velocity distributions found that the available data tended to favor low-density cold dark matter models, rather than an older style of model assuming the universe's matter density alone, without additional contributions from other components, equaled the total critical density needed for a flat universe. This is a fairly technical point, reaching back into the deeper mathematics of cosmological modeling. But its significance, in simple terms, is this: the way galaxy clusters move through space carries real information about the underlying structure and composition of the universe itself. Different theoretical models predict different patterns of cluster motion, and comparing real observational data against these competing models helps researchers determine which broad picture of the universe's contents and evolution fits the evidence more closely. Dark flow research, then, sits within this much larger, ongoing scientific effort, using the motion of galaxy clusters, again and again, across many different studies and many different methods, as one small but meaningful window into the true structure and history of the cosmos. And so, after everything we've explored together across this long night, after the original striking claims, the years of expanding, strengthening evidence, the careful uncertainty about direction, the deeper theoretical possibilities stretching toward inflation and even the multiverse, and finally, the serious, sophisticated challenge presented by the Planck satellite, where does this remarkable story ultimately leave us? The honest answer is this: whether dark flow represents a real, physical cosmic motion, or whether it is ultimately a statistical illusion, born from the immense complexity of measuring faint signals across billions of light years, remains genuinely unresolved. This isn't a story with a tidy, satisfying ending, wrapped neatly around a single, confirmed truth. It's a story that reflects something deeper about the nature of science itself, especially at the very outer edges of what we can currently measure and understand. And perhaps that is precisely what makes dark flow one of modern cosmology's most fascinating scientific mysteries. Not because it offers us a clear, comforting answer about what lies beyond the edge of the observable universe, but because it reminds us, gently and persistently, of how much remains quietly unknown, even now, even with our most powerful satellites, our most careful mathematics, our most patient decades of research. Somewhere out there, hundreds, perhaps over 1,000 galaxy clusters, spread across a vast and ancient universe, may or may not be drifting together, coherently, toward a quiet patch of southern sky near Centaurus, Hydra, and Vela. The evidence has grown, and shifted, and been challenged, and re-examined, again and again, across more than 15 years of careful, dedicated scientific effort. And still, the fundamental question, real motion, or subtle illusion, remains open. There is something quietly beautiful in that openness, I think. In a universe so often described through confident numbers and settled theories, dark flow stands as a gentle reminder that mystery still has its place, that even now, with all of our instruments pointed outward into the dark, there remain currents we cannot fully explain, directions we cannot fully confirm, and edges we may never truly see beyond. Perhaps, somewhere out there, something vast and ancient truly does lie just beyond the edge of everything we can observe, quietly, patiently, leaving the faintest possible trace upon the galaxies we call home. Or perhaps, in time, more advanced instruments will continue refining this signal into nothing more than the ordinary, expected texture of a well-understood universe. Either way, the universe keeps its secrets slowly. And there is a certain peace in that. A permission, perhaps, to simply rest and wonder, rather than rushing toward certainty. Thank you for spending this long, quiet night exploring the mystery of dark flow together. Let the vastness of it settle over you gently now, the galaxies, the ancient light, the silent, unanswered question of what may lie far beyond the edge of everything we will ever see. Sleep well, beneath a universe that is still, even now, so beautifully unfinished.